Our sun, the lifeblood of our solar system, is a dynamic and ever-changing star. It goes through cycles of activity, much like a cosmic heartbeat. These cycles, known as solar cycles, last approximately 11 years and are characterized by periods of heightened and diminished activity. As we journey through the cosmos of 2025, we find ourselves approaching the zenith of Solar Cycle 25, a period of intensified solar activity that has captivated the attention of scientists and stargazers alike. Solar Cycle 25, which began in December 2019, is predicted to reach its peak in July 2025. This means that the sun will be at its most active, with a surge in sunspots, solar flares, and coronal mass ejections. These phenomena, while spectacular to observe, can also have significant impacts on our planet and its technological infrastructure. The sun's activity during this period is expected to be closely monitored by scientists around the world, who are eager to learn more about the inner workings of our nearest star. Sunspots, those dark, cooler regions on the sun's surface, are a visible manifestation of the sun's magnetic activity. They are often the precursors to solar flares and coronal mass ejections, powerful bursts of energy that can have far-reaching effects. Solar flares are sudden, intense bursts of radiation from the sun's surface. These bursts of energy can disrupt radio communications and interfere with satellite operations. Coronal mass ejections, or CMEs, are massive eruptions of solar material and magnetic fields from the sun's corona, the outermost part of its atmosphere. CMEs can travel at speeds of millions of miles per hour and, when directed towards Earth, can trigger geomagnetic storms. These geomagnetic storms, caused by the interaction of the sun's energetic particles with Earth's magnetic field, can disrupt power grids, interfere with GPS navigation, and even damage satellites in orbit. Understanding the nature and timing of these solar events is crucial for protecting our technological infrastructure and ensuring the safety of astronauts in space. The impact of solar storms on Earth is not a new phenomenon. History is replete with examples of how the sun's fury has left its mark on our planet. One of the most well-known examples is the Carrington event of 1859, a massive solar storm that caused widespread telegraph system failures. Telegraphs, an early form of long-distance communication, relied on electrical currents, which were disrupted by the intense geomagnetic disturbances caused by the storm. Auroras, usually only visible near the Earth's poles, were observed as far south as the Caribbean. In more recent times, the 1989 Quebec blackout serves as a stark reminder of the potential impact of solar storms on our modern power grids. A powerful geomagnetic storm, triggered by a CME, caused a widespread power outage in Quebec, Canada, leaving millions of people without electricity for hours. This event highlighted the vulnerability of our increasingly interconnected and technology-dependent world to space weather events. Predicting solar flares and CMEs is a complex task, but one that is crucial for mitigating their potential impacts. Traditional methods relied on observing sunspots and other solar activity, but these methods often lacked the accuracy and lead time needed to take effective preventative measures. In recent years, however, scientists have turned to artificial intelligence, or AI, to improve the accuracy and lead time of space weather forecasting. AI models, trained on vast data sets of solar observations, are proving to be valuable tools in predicting solar flares and CMEs. These models can analyze complex patterns in solar data, identifying subtle indicators that might be missed by human observers. By recognizing these patterns, AI algorithms can provide earlier warnings of impending solar storms, giving us more time to prepare and protect our critical infrastructure. Section 5. Artificial Intelligence, a new era of solar forecasting. One such AI model, developed by Sabrina Guastavino at the University of Genoa, has demonstrated remarkable accuracy in predicting solar storms. In a significant breakthrough, Guastavino's model successfully predicted a major solar storm in May 2024, including an X8.7- class flare, one of the most powerful types of solar flares. This successful prediction highlighted the potential of AI to revolutionize space weather forecasting. Meanwhile, researchers at Utah State University, Sukaina Falali Bubrahimi and Shah Mohammed Hamdi, are developing their own set of machine learning models to predict solar flares. Their goal is to have these models fully operational by the July 2025 solar maximum, providing real-time predictions of solar activity. These models, trained on data from NASA's Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and Japan's Hinode satellite, are expected to significantly enhance our ability to forecast and prepare for space weather events. Section 6. A daring voyage. Parker Solar Probe ventures closer than ever before. While AI is proving invaluable in predicting solar events from Earth, a daring mission is underway to study the Sun up close and personal. The Parker Solar Probe, launched by NASA in 2018, is on a mission to touch the Sun. This groundbreaking spacecraft is designed to withstand the extreme temperatures and radiation of the Sun's corona, providing unprecedented insights into the mechanisms driving solar wind and energetic particles. In December 2024, the Parker Solar Probe will make its closest ever approach to the Sun, coming within a mere 3.83 million miles of our star's surface. During this perilous maneuver, the probe will collect valuable data on the Sun's magnetic fields, plasma, and energetic particles, shedding light on the processes that drive space weather. Section 7. Unlocking the Sun's Secrets. NASA's upcoming missions. The Parker Solar Probe is not alone in its quest to unravel the mysteries of our Sun. NASA has a number of other missions planned for the coming years that will further enhance our understanding of space weather. These missions will utilize cutting-edge technology to observe the Sun from different vantage points, providing a more comprehensive view of our star and its influence on the solar system. These missions will study a variety of solar phenomena, from the Sun's magnetic fields to the dynamics of the solar wind. The data collected by these missions will be invaluable in improving space weather models, allowing us to better predict and mitigate the impacts of solar storms on Earth. Section 8. The importance of predicting space weather in an increasingly technological world. As we venture further into the 21st century, our reliance on technology continues to grow at an unprecedented rate. Our interconnected world, reliant on satellites, power grids, and communication networks, is increasingly vulnerable to the vagaries of space weather. Predicting and mitigating the impacts of solar storms is no longer a matter of scientific curiosity, but a matter of national and global security. The research being conducted by scientists like Sabrina Guastavino, Sukaina Falali Bubrahimi, and Shah Mohammad Hamdi, along with missions like the Parker Solar Probe and NASA's upcoming endeavors, are crucial in our efforts to understand and live with our dynamic Sun. By unraveling the mysteries of space weather, we can better protect our technological infrastructure and ensure a safer and more sustainable future for all. Section 9. Conclusion. A universe of discovery awaits. As we stand at the precipice of the solar maximum in 2025, we are reminded of the power and unpredictability of our universe. The Sun, our nearest star, is a constant source of wonder and discovery. Through scientific inquiry, technological innovation, and a spirit of exploration, we can continue to unlock the secrets of the cosmos and safeguard our planet from the potential hazards of space weather.